Alright folks, welcome to this evening's geometry video. We're going to talk about using inductive reasoning. This part of the class, there's a lot of writing involved, okay, because we're starting to deal with reasoning and logic, and as a result, we have to end up writing some sentences and putting logical statements together. So I'm warning you up front that we're going to have some writing to do, but that's okay. That's okay. We'll get through it. Actually, some pretty interesting stuff that we've got coming here. Let's go ahead and get started here. We're going to be talking about patterns, conjectures, inductive reasoning, obviously, and what that is, and then counterexamples. It's kind of the four big ideas here in this first section. Patterns, patterns, patterns. Mathematics is all about patterns. If you can find a pattern, you can find mathematics. If you've ever seen the movie A Beautiful Mind, I believe it's on a 2-disc set. That movie's about a mathematician named John Nash. But Ron Howard, the director, interviews Mr. Nash, Dr. Nash, I should say, and he says in the interview that he always thought mathematicians thought in numbers. But they really don't. They're just looking for patterns, and numbers are just a way to represent the patterns. So if we look at this series of triangles here, what's the pattern? What is the pattern that we see here? And what would be the next triangle in the group? Well, what I see is that with each one, it's being rotated 90 degrees in a counterclockwise direction. That's what I see. So if I were to find the next pattern, I just have to rotate 90 degrees in a counterclockwise direction, and I would get this. Okay? Patterns, patterns, patterns. There's lots of patterns in many things. In your book, on page 72, there's a pattern with a wheel there. Just looking for different things. Lots of different funky things with numbers. Like obviously some easy patterns. Okay, what's happening here? Well, obviously it's going up by 2 every time, so the next number in the pattern would be 10. Okay, that one's easy. What about this one? Here's a little extra credit for you. If you can give me the next number in this sequence, I'll give you some extra credit, but you got to write it down and bring it to me when you walk in the room for class. Okay? Here's the sequence. Okay? What is the next number in this sequence? That's what I want to know. There's a little extra credit for you. But another pattern that shows up, this one has a special name. But we'll get into that in class. But see if you can figure out what the next number in this pattern is. A little different. A little different. A conjecture, an unproven statement based on observations. The easiest way I have to explain this to you, this is basically a hypothesis for math. Okay? It's basically a hypothesis for math. Now, in a hypothesis, you haven't done your observations before you make your guess. And in math, we have done our observations. But it's basically taking the pattern and saying what the pattern is. So that original pattern we have over with the triangles, okay, our conjecture would have been rotates 90 degrees counterclockwise. That's what's happening every time, correct? If I go back to my triangles, that's what's happening every time down here. The triangles are rotating 90 degrees counterclockwise. Now, if I had my numbers, that first one I gave you, 2, 4, 6, 8, what's happening every time? Well, it is increasing by 2. every time. Okay, now we'll get a little more technical with this as we get into things, but that's basically what you're doing with a conjecture, is you are verbalizing what is happening. Okay, oops, right here. Rotates 90 degrees counterclockwise every time. Increases by 2 every time. 2, 4, 6, 8. A conjecture, hypothesis, but we've already made some observations. We've already seen what the triangles do here. Okay? We've seen the numbers, we know what they do, and we're just telling you what is happening. So it's basically the hypothesis after you've done the research. Okay? Just something to think about. It seems to be easy for kids to relate to a hypothesis as a guess. This isn't a guess, this is just a way to verbalize what has happened. Okay? What is the pattern? Inductive reasoning. Once you have found a pattern and you've written down the conjecture and it works for every single case, you are using inductive reasoning. Okay? There's two different kinds of reasonings we're going to talk about. There's inductive and deductive. Okay? In inductive reasoning, we are finding a pattern. And then we are writing down what that pattern is in a conjecture. Okay? Now, notice this is a specific case. Okay? This pattern doesn't work all the time. It only works in a specific case. Like the 2, 4, 6, 8 case. You can't say that every time I look at numbers they're going to go up by 2. Because that other example I gave you, they didn't. Okay? Obviously that is not going up by 2. So it's not every case, it's just a specific case. Hopefully you understand the difference. Okay, here we go. Last thing, counterexample. Counterexamples you will learn to love. And it is because once we get into proofs, which are coming soon, it's in this chapter. Once we get into proofs, a counterexample is something that will disprove a theorem. And as long as you have one counterexample, it proves the whole theorem wrong. If you're going to have a theorem, you have to prove it for every single possible case. Okay? Let's see if we can find a good counterexample here in your book. Okay? In your book, example 5. The student makes the following conjecture about the sum of two numbers, finding a counterexample to disprove the student's conjecture. This is on page 74. The sum of two numbers is always greater than the larger number. The sum of two numbers is always greater than the larger number. Well, sure, that's true. That's pretty simple, right? Yeah, I start throwing down examples. 2 plus 3 is 5. The sum of those two numbers is 5, and that's obviously bigger than the biggest number. What is a counterexample for this? What is something that proves this wrong? What if these numbers are negative? What if it's 5 plus a negative 3? That gives you positive 2. But is 2 bigger than the larger number? No. This is a counterexample for this conjecture. Okay? It disproves it. This thing is not true because I have found my counterexample over here. 5 and negative 3. If I add those up, the sum of those two numbers is 2, which obviously 2 is not bigger than the largest number, which is 5. Counterexamples. You'll learn to love them because if I can find a counterexample, I can prove it proves it doesn't work. And it's a lot less work than trying to prove that something works for every single case, which we'll have to do too. But counterexamples just make your life easier because you don't have to prove everything. Okay, you just have to find one thing that doesn't work. Okay, hopefully this has been pretty basic stuff. We're going to review this all in class when you get here. We got a fairly short video here, so it'll be easy for you on a Monday night, especially you JV football players. So we talked about patterns. Okay, math is patterns. That's all we're trying to do is find patterns, and then represent the pattern somehow. A conjecture is writing down what the pattern is in words. Writing down what the pattern is in words. Inductive reasoning is once you've found a pattern and you've written it down, you've used inductive reasoning to do that. And then a counterexample is anything that proves a conjecture wrong. And you only need to find one. You find one counterexample, you've proven the whole conjecture wrong. Okay? Again, we will review this when you get to class. Be thinking patterns when you get to class. And don't forget there's that extra credit question I gave you earlier in the presentation. So we'll see you in class, and where we'll go over this again.